All right, guys, am I audible to you?
Yes, sir.
All right. Okay, then let's get started. Turn your cameras on, guys. And I guess you know that in today's session, we'll be starting the conformational analysis, right? So we'll be dealing with the different kind of conformers and how do they affect their stabilities and all the things. That is what we are going to talk about in this session, right? So these kind of questions are really very important. Even in this year's JE as well, we expect these kind of questions are going to come. So and in the last year's NEET as well, these kind of questions came. So that's why, guys, these are the type of a discussion that we need to have over there. Google, turn your camera on. All right. So guys, in the last session, we have talked about those RS nomenclature and stuff, right? So today we'll be starting from the conformational analysis. So this is actually a topic of class 11 hydrocarbon chapter. I guess you do remember learning this particular topic in there, right? Now, both of you guys, you have to be vocal today, because the number of students are right now, they are all having their exams, right? So now, as I was saying here, this is the topic of class 11 that we have learned in there. Now, actually in class 11th, when you learned it, there were only Newman conformer that you have learned in class 11th when you learned it, right? Now, here what we are going to learn is we are going to learn about all the 4 kinds of isomer conformer that can be there. Now, starting from the Newman, Fisher, Sawhorse, and flying twins. These are the 4 kinds of conformer those can be there. So first I would start with the conformer that we have already learned about, which is Newman. Okay. Now, what is this Newman conformer? So guys, in order to understand what is this Newman conformer, what I'm going to do is I'm going to show you with respect to a particular application that I have right now. Okay, I guess you can see this blue screen over here, right? Now, guys, have a look. This is the ethane molecule. Can we really see this? The ethane molecule here, 1 carbon, and there are 3 hydrogens in there, and this is the carbon number, like which is written as carbon number 5. Like this is the second carbon and 3 hydrogens in there. I have given numbers to these things. You can clearly see that. I am going to zoom in. So you can clearly see that they have numbers in there. Okay. So this is my ethane molecule that I have. Now, guys, what I'm going to do is I'm going to add some different atoms in there. So I'm not going to keep it to methane or ethane. I'm going to keep it I'm going to add some chlorine or some bromine or some iodine inside it. All right. Now, see. So first is what I'm going to do is I'm going to add a fluorine in here, carbon number 8. Okay, let's just make it something colorful, not fluorine. Let's just add a chlorine in there. Chlorine is more colorful, right? Now, whatever I'm going to add in this carbon, the back carbon, I'm going to add the same thing in this carbon as well. So this is a fluorine here as well. And then I'm going to keep the molecule like this. Okay, wait. Now see, this is the molecule that I have. All right. Fine. Okay. Now, guys, have a look. Right now, when you look into the molecule in this way, just tell me one thing. Does it look like a horse to you? The thing is, this particular conformer is actually known as sawhorse conformer. I told you there are 4 conformers out there, right? One was Newman, and the other one was Fisher, then sawhorse, then we have the flying wedge. So right now you can clearly see this is actually called Sawhorse conformer. This nothing but looking into the molecule from different angles. Right now, if I just change your way of looking into this molecule, and if I just keep it like this, you're looking from the front. This particular conformer that you see, this is actually known as Newman conformer. So guys, Newman conformer is nothing but looking at the molecule from the front. Now over here, Gokul, what do we see over here? You can clearly see that the front carbon is kind of eclipsing the carbon number 1 in here when I draw it in this way. Right? They're actually eclipsing each other in here. Right? So when we'd be drawing this molecule as well, when you have drawn in hydrocarbon chapter as well, they were eclipsing each other in that position. Right? Now, what I'm going to do is in this particular segment, what I'm going to do is I am going to change the angle. Which angle am I talking about? We call it, tell me, Elizabeth, what do we call this angle, the particular angle by which we rotate the molecule?
Sir, torsional angle?
Torsional angle or dihedral angle. That is what we call it. Okay. So see, what I'm going to do is right now, I'm going to rotate. First, I'm going to keep the angle as 0. So when, guys, the angle is 0 degree, can you see all the similar atoms are eclipsing each other? Means they're just in front of each other. Isn't it, Elizabeth? Like over here, you can see that chlorine is eclipsing another chlorine. Just a sec. Yeah. One chlorine is eclipsing another chlorine. Then one carbon is eclipsing another carbon. The hydrogen is eclipsing the hydrogen behind it. This hydrogen is the hydrogen behind it. So this particular way of writing, when we write it in this way, when we draw it in this way, we say that the bond, the angle between them is actually 0. Now, guys, what I'm going to do is I'm going to rotate the molecule. So let's rotate the molecule now by 60-degree angle. So guys, this is how it looks when the dihedral angle of the molecule is 0 degree. Now, when I move it to 60 degree, now let's see what would happen. So I would like to show you how do I do that. So this is the application, and this is where I am adding 60-degree bond angle. You can clearly see that 60 degree. And then if I click on OK, see what happens. This is the molecule when I'm rotating one of them by 60-degree angle. And this is how it looks like. Now, guys, the molecule before was eclipsing each other, right? That molecule is known as eclipse conformer. Right now, they are not at all eclipsing, right? They are completely away from each other, isn't it? The way you can draw it is there's the front, in the front side, there's a Y, and the back side, there's a Y. Okay, in the front Y is inverted, the back Y is just the way you write Y itself. Right, Gokul? Clear? So this is how we draw the when we draw the molecule by 60-degree angle. This is how it's going to look like. Now, guys, what I'm going to do is now I'm going to change the angle by 60-degree more. So what will be the new angle then? 120 degree, right? So let's keep it in
Yes,
here
sir.
and let's see what happens in 120. Okay, let me just show you how the path changes when I'm taking it to 120. Just look into this. Okay, from 60 degree, I'm increasing the angle and see how the molecule is changing, how the molecule is rotating. All right. And when the angle reaches 120, see, I am going to reach another eclipse conformer. You'll be able to see it in 2-1. There you are. You can see this is again another eclipse conformer, isn't it? Not like the previous one, but this is also one molecule is eclipsing another. Don't you agree with this, guys? One atom is eclipsing another atom here as well. So it is also kind of an eclipse conformer where one atom would be eclipsing another atom, but not exactly the same like the way you have seen before. But yeah, similar, something similar like that. Isn't it? Clear so far? Both of you?
Yes, sir.
Great. Okay. Now, Okay. So now what I'm going to do is, I'm going to now rotate the molecule. I'm going to rotate this molecule again. Now this time by 120-degree angle. Now let's see what happens. If I rotate the molecule by 120-degree angle. So let me show you right here, the top of it. Okay, I'm rotating the molecule by 120-degree angles. So 60 and then, okay, we did it to 120 only, na? Before.
Yes, sir.
Now we'd be going for all the way to 180. You see how the molecule is rotating. Can you see this? So I'm rotating it to all the way to 180-degree angle. Now see how the molecule looks like when the rotation is 180. See here, similar atoms are opposite to each other, completely opposite to each other. So what do we call this conformer over here, Elizabeth?
Staggered.
Definitely staggered, but what kind of staggered? Any specific kind of staggered?
Sir, like maximum staggered.
We call it anti, because you can clearly see that similar atoms are opposite to each other. All the similar atoms are opposite to each other, right, Gokul? So this is called anti-conform. Okay. So now let's get back to let's just draw these molecules now and see how to do that. And on the basis of this, what we'll be doing is we'll be solving the previous year questions on the basis of that. Okay. So first, what was the molecule we were really dealing with? Let's say we have CH, H, then we have a Cl in one molecule and one carbon, and the other carbon was like this. Right. Then you draw the Newman projection of this. So in the Newman projection, let's say this is carbon number 1 and this is carbon number 2. We'll be drawing only carbon number 1 because this is where we are looking at it from this side here. So we'll only be able to see only carbon number 1. So this is the carbon number 1. In carbon number 1, you can clearly see this is how the 3 atoms are arranged. So chlorine, hydrogen, hydrogen. And carbon number 2 as well, chlorine, hydrogen, hydrogen. What do we call this particular conformer, guys? This is called eclipsed, right? Total eclipsed. So this is how we draw the Newman projection. So right now, what I'm going to do is I am going to form the Newman projection of ethane of this same molecule only, and I am going to rotate the molecule a little bit and to see what would be the more energetic molecule and what will be the more energetic conformer and what will be the less energetic conformer. That is the work we are going to do here. Okay, the molecule that I am dealing with right now here is actually CHFCl, CCl, H. So there are two substituents in this molecule. That's an ethane molecule where I have substituted 2 of the hydrogens with fluorine and chlorine. Okay, I'm going to do the Newman projection of this molecule. So guys, carbon number 1 is what you're gonna see. So carbon number 1 is this one, and you can see that clearly I have maintained the arrangement here, similar to the way I have drawn in this conformer. So this is the way of drawing Newman conformer. Now, after drawing the Newman conformer, what you have to do is you have to keep on rotating the molecule. Okay. Now, when you rotate the molecule, when the angle is 0 degree, what did I tell you guys at that time? When the angle is 0 degree, everyone is eclipsing each other, isn't it? In the just before that, I have shown you in the diagram over there, right? So everyone is totally eclipsing together. So when it is 0 degree, we call it total eclipse or fully eclipse. Same thing. Total eclipse or fully eclipsed, right? Now, when we rotate the molecule by 60 degree, over here, Gokul, would you be able to tell me what is the angle between these two bonds?
Sir, 120.
That's correct. So if I rotate the molecule by 60 degree, then what would happen is this, I am rotating the back carbon. All right, guys, I'm rotating the back carbon. So I'm rotating carbon number 2 here. So if I rotate the carbon number 2, then what would happen? The this hydrogen would come in the middle portion somewhere here, because I'm rotating but 60 degree right now, not 120 degree here. So 60° means this is where the hydrogen would be. New position of the hydrogen would be. The back fluorine would be now coming halfway here, somewhere here, and the chlorine would be coming halfway in here somewhere. So if I rotate the entire molecule in the clockwise direction by 60° rotation, then this is how the molecule should look like. Did we get this?
Yes, sir.
Great. Now, again, if you rotate it to clockwise by 60° more, which means you are going to 120°. So this is when the dihedral angle is 60°. Okay, what is this angles again? You can call it torsional angle or dihedral angle. Dihedral or torsional angle, anything. Right, Gokul? So over here, when the dihedral angle is 120°, then how it's going to look like? See, now you rotate it to 60° more. 60° more. So the hydrogen would be here, fluorine would be here, chlorine would be here. So here is what I'm going to write my hydrogen, and behind that I am going to write the chlorine. Behind this I'm going to write hydrogen again, and behind this, right? This is the second eclipse conformer, but this is not exactly the total eclipse. This is also eclipsed, but two different molecules atoms are eclipsing each other here. Now again, guys, if I rotate it by 60°, then what would happen? Then again, the back, I'm only rotating the back carbon. Then the fluorine would come somewhere in between here. The chlorine would come somewhere in between here. And the hydrogen would come somewhere in between here, giving me this particular. I want all of you to draw all these conformers that I'm drawing here. Because on the basis of this, I would tell you what would be the stability order of the conformers. Okay, then that is the kind of a questions that they would ask you guys. So draw all these conformers with me. So when I rotate it by 60° more, it was already rotated by 120°. Now I am rotating by 60° more. What would be the total angle then? 180°. Right, guys? Clear?
Yes,
now,
sir.
Yes. Now, what did I tell you? When the rotation is totally by 180°, what is the name of the conformer? When the similar atoms are exactly opposite to each other. What is the name of the conformer? This is called anti-conformer, right?
Anti-conformer.
Great. It's called anti-conformer. So this particular conformer is actually known as anti-conformer. Right, guys? Now just give me 1 second. In the meantime, you just draw the rest of the conformers on your own. All right, guys, are we done? See, now what is happening in the next section over here, segment over here? Here it is, you are rotating the molecule again by 60 more degrees. So the fluorine would come here, the chlorine would come here, the hydrogen would come here. And again, it's an eclipse conformer. Eclipse means when just the way you see lunar eclipse and all those things in the same way. Okay. So this is also another eclipse conformer. Then again, I rotate it by 60° to go to 300°. Now, guys, I guess you are being pro at it. So 60° means again halfway rotation. That gives me this molecule. And then again, a rotation gives me this molecule. So back to 360 rotation. 360 rotation means, guys, the angle is now from 0 to 360 means I'm coming back to the same molecule again. Right. So let me just show you one more time with the help of the ball and stick model real quick. I want you to understand this really very vivid, in a very vivid manner, because we are expecting these kind of questions to come in this year's NEET. All right. So let's make the molecule that we were dealing with there. So we had one hydrogen in there. right? You can clearly see ethylene, 2 carbons and one hydrogens in there. Then what else was there? There was a chlorine connected to it, right? So I'd be adding 1 chlorine in there then, which is a blue colored molecule atom. All right. Then there was a fluorine in there. So I'd be adding 1. Fluorine in. Guys, you can clearly see the bond length of CCl would be more than the bond length of C and F, isn't it? That's why CCl bond length is more. You can clearly see from here. CCl bond length is more, CF bond length is smaller. All right. Now, we're doing the same thing here. Would be considering this in a way that we don't have to study it again before our NEET. So make sure you pay attention in that way. Okay. Now have a look. This particular conformer, when you look at it, this is actually Sawhorse conformer. When you look at it from the sideways. Now, when you turn it around and look into it from the front side, this is called Newman. And guys, this is when the dihedral angle is 0 degrees. 0 degree. Just a second. Yes. This is when the dihedral angle is completely 0. Right? You can clearly see that this is a total eclipse right now. Like this fluorine is eclipsing that fluorine, this chlorine is eclipsing this chlorine, and this hydrogen is eclipsing this hydrogen. Total eclipse. Right? Now, if I rotate the back carbon, the one I am holding on, if I rotate it by 60 degree along the dihedral angle, this is how it should look like, right? And that's how you have drawn this. Then if I rotate it by 60 more, again another eclipse. If I rotate it by 60 more, these are the conformers, guys, we were drawing in the board, right? 60 more. Total, we have 280, 240. This is 300, right? And this is conformer of 360. You can completely look into the molecules again, the way I have rotated this. You can look into it and find it. Right. Now, it's time we talk about their stability. Okay, before we do that, there is one more thing that I would like to tell you. When the conformers, when they look like this, when they're not eclipsed, when they look like this, then this situation, Gokul, no, not it. In this conformer, when they're not eclipsing each other, all right, in this conformer, like this one, this type of conformers are known as staggered conformer. Okay, so this is one staggered, this is an eclipsed, this is anti, or this is also a staggered conformer, but anti is much more, detailed answer. Then this is eclipsed, this is also staggered, and this is also eclipsed. So just a simple question to you guys. Would you just write it in the chat? What do you think? Which conformer, which kind of conformers are more stable? Is it the eclipse conformers or is it the staggered conformers? Which kind of conformers are more stable? Yes, that's correct. What about others? Guys, everybody has to reply to this question. Come on, be quick. Which conformers are more stable to you? Is it the eclipsed or is it the staggered ones? Yes. The staggered ones are the most stable. Because guys, have a look again. In this particular geometry, when they are right behind each other, there is a steric repulsion. They are repelling each other. Okay. But when they are like in this way, there is no such steric repulsion, which is steric repulsion, which is working in there. Right. So that's why this particular staggered conformers are always more stable. Did we get that? So guys, all the staggered conformers are always more stable. Now the question is, out of the staggered conformers, which particular staggered conformer is the most stable conformer? So you have options like 60-degree one, 180-degree one, or 300-degree one. Which particular staggered is the most stable staggered? What do you think, guys? Write it down in the chat. Yes, very good. That's the right answer. Anyone else? Which particular staggered is the most stable staggered conformer? Definitely the 181, because there the molecules are exactly opposite to each other. So anti is the most stable. So guys, right now what I would do is I would try to draw the potential energy diagram over here. Now here what would happen is the 180 staggered conformer is the most stable, so it would be having the least energy over here, right guys? So that's why I'm going to put it. Now right now, out of the eclipse conformers, would you be able to tell me, guys, which eclipse conformer is the most unstable eclipse conformer? Is it the 0-degree one, or is it the 120-degree one, or is it the 240-degree one, or is it the 360-degree? Which one is the most unstable eclipse conformer? What do you think? That's right, Elizabeth. 0 and 360-degree. These two are the most unstable ones. Now, why is that again? See, look into this diagram, look into this model real quick. When the eclipse, like I said, when it is a total eclipse, the similar atoms are eclipsing each other. This particular situation is the most unstable situation for a molecule. And when the similar atoms are exactly opposite to each other, means in 180-degree, which is the anti-conformer, that is the most stable situation. So let's write it down here. Fully eclipsed or total eclipsed is the most stable conformer, and anti is the most, sorry, this would be unstable, right? Unstable conformer, and anti is the most stable conformer. So if fully eclipsed are the most unstable conformers, so guys, they would be having the highest energy. And where do we have the fully eclipsed conformers? We'll just have a look in these diagrams. In 0-degree, I have a fully eclipsed or total eclipse. In 360-degree as well, we have a fully eclipsed or a total eclipse. You can clearly see that the chlorines and the hydrogens and the fluorines are eclipsing each other. So considering that, these two are the situations where you have the total eclipse going on. As a result, guys, 0-degree and 360 has the highest energy where I have kept them. All right, understood? Now, let's come back to the staggered ones. So guys, we have just learned that the staggered conformers are more stable than eclipsed. We just learned that the staggered conformers are more stable than the eclipsed conformers. We just learned that. So the staggered conformers, those are there in angle number, which all staggered we haven't talked about, angle 60, and the other staggered that I have on angle 300. These are more stable than the other conformers, other eclipsed conformers. these two staggered are more stable. So where would I put them? The 60-degree and the 300-degree staggered conformers are going to be here. Now, why is that? See, this 60-degree conformer and 300-degree conformer, they are staggered, right? But they are not as stable as anti-conformer. So anti is also a staggered, but anti being having a situation where the similar atoms are opposite to each other, this is the most stable staggered. So that's why I'm keeping anti at the bottommost port position. Then a little bit more energetic are the normal staggered ones. Okay, they are also stable, but not as stable as anti. A little bit more destabilized than anti. Then comes the eclipsed ones. Now, guys, the eclipsed ones are 120-degree eclipse. So at this position, you have an eclipse, and preferably in 240-degree, you would be having another eclipse. Now, guys, these eclipsed conformer are destabilized. They have high energy, but not as high as total eclipsed. Right? So where am I going to put it? Somewhere here, a little bit lower than the total eclipse. And 240 would be right. So total eclipse has the highest energy, which is 0-degree and 360-degree. Then comes the normal eclipse. Then comes the normal staggered. Then comes the anti-conformer. Now, guys, how would the energy profile diagram look like? Are we clear? This is how the energy profile diagram is going to look like for our conformational analysis. Are we all clear over here, guys? Just write it down in the chat, because right now I'm going to take you to the previous year questions. If you still have any sort of doubts, just write it down in the chat. And what about others? Amita, Amrita, Gokul, we're all clear, guys? So far, how the diagram and everything came in? Great. So let's solve the question then. Okay. The question went like, the most stable form of meso 2,3-difluoro 2,3-butane is. So what they're saying is, there's a meso compound. Do we know what is the meso compound? Elizabeth, do we know what is the meso compound?
Sir, the mesoform compound.
What?
Sir, like there is a sigma plane and it's optically inactive.
Yes, there is an sigma plane and optically inert, right?
Yes, sir.
Yes, that is correct. Okay, would you just tell me one thing? Is my voice clear and audible? Like, is it loud enough for you to understand?
Yes, sir.
Okay. Now, meso compound is a compound which has a sigma plane in it. And what is sigma plane and all? This is something you have learned in the chapter called haloalkanes and halogens, right? So, anyways, guys, right now that is not our point. Our point is I have a molecule which is meso 2,3-difluorobutane 3-diol. Okay, so this is the molecule that you have. You have 4 options. What you have to tell me is which one is the most stable form. Is it form A? Is it form B? Is it form C? Or is it form D? Which form is the most stable form of the molecule? So guys, try this one, all of you. You'll be getting 2 minutes to solve this question. All right, Gokul. All right, Elizabeth. And what about others? What do you think? Which one is the most stable so far? Okay. You might be thinking that option C is the correct answer, right? You might be thinking, because considering, you might be thinking the option C is the correct answer considering it's an anti-conformer, right? They're opposite to each other, and I just told you guys anti is the most stable situation, right? But if you write option C, that is a wrong answer. Now, why is that? Because there is a huge thing which you are missing right now. Thing is, in this particular system, option A is the correct answer, which is not an anti. It's a staggered, but not anti, but still it's the most stable conformer. Do you know why, guys? Because this molecule over here is capable of making hydrogen bond. So as this molecule is capable of making hydrogen bonding in this molecule, that's why the anti-conformer is not the most stable conformer. This particular staggered is the most stable conformer. Do we get this? Come on, guys, just answer this now. Do we get this? Like, why is this the most stable conformer? It's not the anti, but still the most stable conformer, because there is a hydrogen bonding which is getting performed in here. Understood, everyone?
Sir, so like the hydrogen bond will only consider the stability.
Yes. So this is what I'm going to tell you now. For the systems which can undergo hydrogen bonding, those systems are more stable in Gauch conformer. This conformer is known as Gauch conformer. I'm going to show you what is Gauch conformer. Is more stable in Gauch conformer. What is Gauch conformer? Gauch conformer is somewhere where the two similar molecules are beside each other. It's also a stable staggered form only, but two of the similar molecules are beside each other, not behind each other, beside each other. A staggered where two of the similar molecules are beside each other. So here we can make the hydrogen bond. So for these kind of molecules where the hydrogen bonding possibility is there, for them the Gauch conformer is more stable. So this is one of the example. Which else? What else can be another example here? Like, guys, I can put a amine group in there, right? I can give a amine group in here. There also we'll be able to see hydrogen bonding. Who can show hydrogen bonding? F, O, and N. So whenever I have any one of these three elements, we would be considering that the Gauch conformer is the most stable conformer comparative. Is that clear to everyone?
Yes.
Okay then. Let's try to solve this question now. Which of the following is a meso compound? So guys, there are option A, option B, option C, and option D. They are saying which of the following is a meso compound. What do we mean by meso compound? Let me just give you one small example of it. In the meantime, if you know the answer, you just try it. What is a meso compound? The molecules having sigma plane on it. Okay. The molecules those are having sigma plane on it, they are meso compounds. As an example, tartaric acid guys, have you seen these kind of conformers before? The way of writing, this way of writing, have you seen it before? This is the Fisher, right? In biomolecule, you have learned it. This is the Fisher conformer. Now, anyway, over here, what happens is you can clearly see there is a mirror plane in the molecule. The top part and the bottom part is mirror image to each other, like this part and this part. It's like there is a mirror inside the molecule, right? In a horizontal plane. So this is called a sigma plane. So whenever you can break a molecule into two halves with the help of a sigma plane, that's a meso compound. And a clear example of that is we, like the humans. Over there, if you just cut yourself from right between your nose, the right side of your face and the left side of your face, they are similar, right? They are mirror images to each other. That's why, guys, this is called a meso compound as well. So, guys, what you have to do is out of A, B, C, you have to find that whether you can see a mirror plane in the molecules or not. If you see it, then that's a meso compound. Okay. If you want to solve this question, first you draw, for all of them, you draw the eclipse conformer. For all of them, guys, draw the eclipse conformer. Okay. That can help you out. Draw the eclipse conformer. Like the total eclipse, if you can. Try to draw the total eclipse conformer in all three of them. And tell me what you get. Total eclipse means similar atoms would be behind each other. Try to draw this. Done. How will the total eclipse conformer of this molecule look like? Total eclipse means, tell me guys, by how much angle do I have to rotate the molecule? The chlorine bond, if I rotate it by 180 degrees, isn't it?
Yes, sir.
So if I just take this chlorine all the way to this, then it is a total eclipse conformer. So try to draw the total eclipse then. So rotate the backside molecule by 180 degree now. Okay. Then now, if I rotate the molecule, back molecule by 180 degree angle, so the chlorine would be exactly to the opposite side of it, whatever it is. So here, would it be? The hydrogen would be exactly opposite to that side where it is presently situated. I mean the back hydrogen. Sorry, I'm rotating the back carbon. Okay. Exactly the opposite side. Here, and the CH3 would be exactly the opposite. So guys, this is the total eclipse conformer. Now you can clearly see that right now there is a mirror going right between them. Okay, there is a sigma plane present, which is cutting the molecule from right from the middle. Let me show you how. This is how the total eclipse is looking like, right? Now you tilt it in this way. And now you break the molecule from the between. Do you see that this side of the molecule is the mirror image to this side of the molecule? Let's have a close look on it. Isn't it? This end and this end feels like there is a mirror right here, right? So there is a sigma plane in this molecule. Try to draw the total eclipse of this molecule and see whether you can draw it or not. You won't be able to draw it. Try it. Are you being able to draw the total eclipse of this molecule, guys? We can't draw it for B and C exactly. So if you try to draw the total eclipse by keeping the chlorine behind each other, let's see whether we can draw it or not. So keep the CH3 on the top, chlorine in here. Try to take the chlorine behind this chlorine. Means by which angle are you rotating it? 60 degrees. Then this CH3 would be here. And this hydrogen would be here. So guys, you cannot really draw the total eclipse. So that means there are no sigma planes in here. If you could draw the total eclipse, then there was a sigma plane. As you cannot draw the total eclipse, that means there is no sigma plane in this molecule. Same goes for this. Can you draw the total eclipse for this? Keep the chlorines together. Chlorine. Then the hydrogen would come here. And the CH3 would be coming here. Is there any sigma plane, guys, that you can draw that you can go right between? See, there is CH3 and H. If I cut if I say that there is a mirror, CH3 cannot be having a mirror image as H, right? So CH3 mirror image would be another CH3 molecule. So that means there is no sigma plane in this molecule as well. So there is only one sigma plane in this particular molecule. So guys, the answer is option A, which is a meso compound. Are we all clear, guys? Just write it down in the chat. Are we all clear with this question? Great. Now there is something that I'm going to start right now, but I'm not going to give you the PYQs today. Okay, the PYQs would be taught in the next session. In the conformational analysis, there is another type of molecule that is being taken under consideration, which are known as cyclohexanes. So guys, conformers of cyclohexanes are also very, very important. Okay, there are 4 conformers that a cyclohexane can be drawn. So guys, cyclohexane looks like a 6-member ring, right? But in reality, this is not how it looks like in real life. Is there anybody who can tell me how the cyclohexane molecule looks like in reality? Is there anyone who can tell me the answer? What is the real way of drawing the cyclohexane molecule? Is it like the benzene, the way we draw benzene? Or is there any other way of drawing it in reality? Do we know this?
So like there's no double bond in between, so
Yeah.
it's just a ring compound.
So just like this is the right way of drawing, you're saying?
So like should we write CH instead?
No, I'm not talking about that. But this shape that I have drawn, this is not the exact shape in which the cyclohexane molecule resides in the nature. It resides in 4 different shapes, and that's what we needed to know. First shape is this. Carbon number 1, carbon number 2, carbon number 3, 4, 5, and 6. 6 carbon, cyclohexane. The cyclohexane can be found in this way, the way I have drawn it. This is called chair conformer. Second, it is also found in this way. This particular way that you can draw, it is known as the boat conformer. As you can clearly see, guys, this is looking like a boat, right? So it's called boat conformer. Okay. This also 6 carbons are there. 1, 2, 3, 6 carbons are there. There are another way in which we find them, which is called, do we know what we call this conformer? It's called half chair. You can clearly see that it is not exactly the way chair conformer looks like. So it is going to be called as half chair. And there last another conformer in which we have found it. It's called twist boat. Six carbons. So what do we call this? Twist boat. So chair, boat, half chair, and twist boat. This is what we are going to talk about, guys, in the next session. But before I leave today's session, I will just tell you the order of their stability as well. All right. So if I draw an energy profile diagram right now, okay, with respect to potential energy, always remember the chair conformer. This conformer is the most stable conformer. This is the most stable chair conformer. Then after that, the next conformer is chair is the most stable. Then in this energy, we found the twist, we find the half chair. So this is the conformer number 1, which is chair. This is the conformer number 3, half chair. Twist boat is here, which is conformer number 4. And boat is a little bit more than twist boat. So guys, this is the exact way of drawing them, and this is the energy profile diagram for them. Now, these questions are really, really very famous questions. They do ask you, giving you option A, B, C, D, what is the energy order of the different conformers of cyclohexane? So the most stable conformer is the chair conformer. Chair conformer is the most stable. Then after that, after chair, twist boat. Twist boat is the second most stable. After that, guys, boat. And the least stable conformer is half chair. So this is what we are going to discuss in the next session. All the sessions are really very important for your NEET preparation, guys. I do know that your exams are going on, but try to attend these sessions for the next few days. On the month of February, we'd be closing these sessions, and then onwards, you'd be completely focusing on your board preparation. For the time being, just come to all the sessions over here, guys, for all this physics, chemistry, and bio. All the sessions are going on here. These are really important, and these are the other topics that you don't really learn in the boards level, right? So this is where we stop it, and the next section, guys, we'll be talking about these kind of conformers and their energy related questions, PYQs as well. So that is it for today. Then bye everyone. Good night to all of you.
Thank you, sir.
Welcome. Bye.